Good evening, everybody. My name is Kristen Gonzalez-Vega, and this is AP Physics C, Electricity and Magnetism Live. We are back. It is Monday, and I have my friend Roger here. Roger, you want to say hi?
Yeah, hi everybody. My name's Roger Siegel, and I am coming to you from Sarasota, Florida.
Okay, so today we're going to do a little bit more of Gauss's law. So we did some the other day. We did a lot of conductors. Today we're going to focus a little bit more on insulators and also kind of touching back on what exactly is electric flux. Again, I am Kristen Gonzalez-Vega, coming from Frisco, Texas, and we have Roger with us from sunny Florida. So our objectives today are similar to what they were the other day. We want to be able to calculate the flux through an arbitrary area. We want to qualitatively apply Gauss's law to a system and state and use Gauss's law in integral form. So just as a quick little review here, let's talk about what electric flux is. We used the analogy of the sunlight the other day on how we can compare, and that flux is really just a flow of some quantity through a surface. So electric flux is the electric field through a surface area. So we can find flux two different ways. We can find flux because it is the integral of the electric field. Dot dA, we can also use the Q enclosed over epsilon naught. So there's two different ways we can find that electric flux. And if we put both of those sides together and equal them, that gives us Gauss's law. So Gauss's law is that the closed integral, surface integral, of our Gaussian surface of E dot dA is equal to the Q enclosed over epsilon naught. So we're going to do a little bit more practice here. I have a charge Q that is far from all other charges, and we have two surfaces drawn here, right? These are two Gaussian surfaces, S1 and S2, and they are spheres centered on Q. The radius of S2 is 4 times the radius of S1. So I'm going to go ahead and label that this, we'll just call this R, and I know that this one is 4 times that R. Okay, so I want you to take a second here and explain to me how the electric field compares at surface 2, right? If we know that the electric field at A is E1, let's just call it, you tell me what is E2 compared to E1. Okay, and then also compare for me the flux through surface area 1 and surface area 2. So I'm going to give you just a second here. If you can give me those two answers, and then we'll go over it. So compare those electric fields and compare the flux through the electric flux through those two surfaces. So if we want to be able to compare the electric field, we need a relationship, right? Anytime we want to go back and forth and compare quantities, if we're changing one variable or another, we've got to know what our relationship is. And so we've got to first use Gauss's law to get an equation for the electric field as a function of radius. So I'm going to do it up here where I have a little bit more space. So if we start with Gauss's law, that the integral of V dot dA equals Q enclosed over epsilon naught. Remember, we're always looking at those two things that we got to plug in for Gauss's law. It's always just those two things. So if we take the electric field, and if we draw this, if I draw it a little bit more 3D, right? If I take one little surface area here, or one little surface area here, and we look at that electric field going out, then anywhere on that one surface, if we're equal distance from that charge, should have the same magnitude of electric field. So the direction is going to be different, but the magnitude of the field should be the same. So that is why if you apply that symmetry correctly and you use the right Gaussian surface, you should never ever have to actually integrate across your surface for the electric field because it should be a constant. Okay? So that just becomes E. If we look at the A, if we take the integral of all of the little surface areas across that, that's the whole surface area of our Gaussian surface. And since this is a sphere, then we can say that this is 4 pi r squared for any r. That equals, if I look at what charge is enclosed in my whole Gaussian surface, it is little q. So that becomes E is equal to Q over 4 pi epsilon naught r squared. So if we look at the relationship, what kind of relationship do the electric field and the radius have? Well, it's an inverse square relationship. So if the electric field is E at point A, and this radius is 4 times as great, well, if I put in a 4 over here, and that radius is squared, then the charge isn't changing, so that stays as a 1. So 4 pi epsilon naught, that's all constant. So really I'm looking at 4 squared, which is 16. So the electric field at position 2 should be 1/16 the electric field on that first surface. Okay, but what about the flux? Let me erase some of this here. Let's compare the flux on the two surfaces. How can we get flux? Well, there's two different ways we can look at it, right? So I always kind of write them both down and then I look, well, what do I know or which one is going to be easier for me to use? All right, so we know the electric flux is either two things. It's either the integral of E dot dA, or I could also use Q enclosed over epsilon naught. Easiest one to always go for if you can is the Q enclosed over epsilon naught, because all you need to know is the charge, because epsilon naught is a constant. We change the field, we're going to change the area, but we can look at that too, because I already know what happened to the field at that part. So I know that the area is related to 4 pi r squared. So if this has 4 times the radius, well, r squared, that means it has 16 times the surface area. But we already determined that it has 1/16 the electric field. So we can see 16 times 1/16, we get the same amount of flux. Let's check the Q enclosed over epsilon naught side. If I look, what charge is enclosed by surface area 1? It's little q. Well, what charge is enclosed by surface area 2? It is still little q. So the charge is the same in both cases, which means our flux is the same. So if it was just flux the first time, it's still going to be just that flux. Same flux, or we would multiply by 1. Okay. So I'm going to toss it back to Roger to do a couple more practice problems with you guys.
All right. Well, thanks a lot, Kristen. All right. So we are going to share the screen and bring up the slides here. And so what we want to look at now is a couple of problems. First one is a problem here. It has to do with a line of charge. It says a very long rod carries a uniform charge density lambda. We talked about that last week. And just to recall, lambda is a charge density. It's coulombs per meter. Okay. All right. So two Gaussian surfaces shown are S1 and S2. We can see up here are cylinders that are concentric to the rod and have the same length. The radius of S2 is 5 times as much as the radius of S1. So you can see here's the radius of S2 all the way out to here. And you can see this is not to scale. All right, so the first question says the electric field at point P on the lateral of S1 has a magnitude of E. What is the magnitude of the electric field at a point Q? All right, down here, which is on the lateral side of S2. So here are our two cylinders, our two cans, and we're going to find the electric field. And so what we're looking for here is what is the electric field? If the electric field here at point P, okay, is, what did we say that was? That field is E. Then what is the electric field from the same charge, from this charge at this point? What is that field? You know, what is its relationship? How much more, how much less? Is it the same? And so what we would do is we would look at our Gauss's law. Now remember, Gauss's law, we have to have symmetry. And so what's symmetric around a long linear charge is a cylinder or a can. And so our cylinder is here. And we can see that the ends of our cylinders, because of symmetry, because of the radial nature of the electric field, the ends have no flux through them. And so when we use Gauss's law, E dot dA is equal to Q enclosed over epsilon naught. We set up symmetry so the E can come out front, and then we're going to add up all the dA where we do have an electric field. And that is all along the lateral or the side of the can, if you will, the cylinder. And if we recall from previous problems, this is pi r squared L. If I call L this distance here, now you could say, well, How can you put an L there if it's not already in the problem? And here's what's going to happen. It's going to go away. And so that is our area. And on this side, we have our Q enclosed is L lambda, because that's length times charge per unit length. So that's the charge, and epsilon naught. And I told you a second ago that the L's were going to cancel, and indeed they do. And so we get that E is equal to L. I'm sorry, did I do that? I sure did. I canceled the wrong thing. Let's see if we can back that out. Okay. All right, let's cancel the correct thing. We are canceling the L. And so we have E is equal to lambda over pi r squared epsilon naught. Now, so what does that tell us about the, I'm sorry, this is incorrect. Let me fix this. I got to look at my notes. I said that this was the area, and I made the mistake of putting the area of a circle instead of a circumference. So this is 2 pi r. Okay, there we go. And so let's come back here. And so we can see that the L's cancel. And so this is, I knew that was wrong when I saw the R, because the answer to this is R to the 1. The previous one was R squared. Why? This is a cylinder. The other one was a sphere. And so that is our reliance. So if we have a 5-fold increase in the radius, what do we have in the electric field? Well, that's going to be E over 5. Okay. Now, the next part we can do very quickly. What did we just learn in the previous problem up here? We saw in this problem that the flux was the same through A, the same through B. Why? Because the flux depends, even though Gauss's law is over on this side, E dot dA is equal to Q enclosed over epsilon naught. This is Gauss's law. Don't forget, this is the flux. This is the electric flux. And so if we can say what that is, we can easily figure out, well, as I get a bigger cylinder, I'm not changing the Q enclosed, so the flux is the same everywhere outside of the radius of our charge. Okay. Now the next one we have is a little bit tougher. I'm going to take a little bit take this one a little bit slower because it involves a 3-dimensional integral. Okay, so we're going to take a look at this. There's a lot of symmetry. We're not going to have to integrate 3 times, but you'll see. Okay, so the problem says a spherical cloud of charge has a radius r equals 5 meters, carries a positive charge that is not uniformly distributed throughout its volume. The charge density is given as a function of the distance r from the center by rho is equal to 30 pi r if r is less than r and 0 if r is greater than r. So what are we saying here? I'm going to draw a graph whose axis is the same as this big R. And so out here we have big R. And I'll go ahead and zoom in a little bit so we can get this kind of big. All right, so now what are we saying about R? What are we saying about the density here? Well, you can see that the density is 30 pi over R. So let me go ahead and write that there. Density is 30 pi over R. So what does that mean? Well, you can see that's an inverse function. So here, this goes to infinity it's asymptotically at infinity, but it falls off as an inverse function. So what does that mean? Well, let me actually do that a little bit different. So that means that as I go out, I have a less dense charge. So how does that mean? How am I going to figure out how much charge I have enclosed? Because I'm going to have to use Gauss's law to figure out how much charge I have enclosed. Well, that's the first part of this problem, is finding out how much charge we have enclosed. And that's kind of challenging. What we have to do is we have to take these tiny little dRs, right? We're going to integrate, and each little thickness of this is a very, very thin dr. And at that thickness, we know the density. And so what we will do is we will make a spherical shell. We're going to integrate these by spherical shells. All right, so let's give this a try. I'm sure this is something you've seen in your calculus class, and we're excited to do it again here. Finding my notes. Okay. All right. So the first thing I want to say, it says write an expression for the total charge. So let's get started here. So the total charge, Q, okay, is equal to, actually, let's say that the total charge will be capital Q. The total charge, capital Q, is going to be equal to the density times the volume. Now that's the density if it's the same density uniform everywhere. But we know it's not uniform. And so what we've got to do is we've got to find out every little dq to find the charge and add them all up. And so that's going to be rho times dv. All right, now let's talk about what this is. This is our density function, 30 pi over r. This is a tiny little volume of a spherical shell, and its volume is the area of the sphere, which is 4 pi r squared. That's the surface area of my spherical shell times its thickness, this tiny, tiny little thickness. And if I had more time, I would be peeling an onion out for you, and I would take a real translucent layer of an onion. I would say, see how thick that is? That's what we're talking, very, very thin. And so if we can add up all these dq's like this times this, we can then get our charge, our total charge. So what we're going to say is over here, we're going to add up Q, and that's going to be the integral of rho. Well, let's go ahead and say what rho is. Rho is 30 pi over r. I'm sorry, 30 pi times r. How could I have done that wrong? I am so sorry, ladies and gentlemen. Let me fix this. I didn't look at my notes. Okay, so my R is increasing as I go out. The reason I thought it differently is because I was thinking of a more natural situation. Okay, here we go. This is mathematical, not physical. All right, so that is, let me fix that then. That is 30 over pi times R. And then we have our area, which is 4 pi r squared times dr. And we're integrating that from 0 to some radius r. I don't want to call it a radius r. Let me call it x for this. I don't want to change this. I could change this to x, but I'll go ahead and set this here. Now, what you can see is the pi's are going to cancel. I'm going to get 120 out front. And I'm going to have the integral of r cubed dr from 0 to some outside distance x. We'll change it to r in a minute. And so this becomes 120 times 1/4 r to the 4th from 0 to x, or 30 x to the 4th. Now I'm going to change it back to r. So I'm going to say q as a function of r is equal to 30 r to the 4th power. Okay, and when we look at this, that should make sense, because as we go up over here, as we move out, we have more density. We have a denser situation, and what that means is more density, and we also have a bigger surface area the further we go out. So we expect this to increase by r to the 4th. All right, so now let's see what happens if we go over here and we have r is greater than r. Well, once I get bigger than once I get past the outside of this sphere, what happens? Well, my density is 0. It's right here. My density is 0. And so since my density is 0, what I'm going to do is I'm going to say that we have Q at R is equal to or greater than r is 30r to the fourth. All right, let's get through this. We're almost home. Now we can use Gauss's law because we've got the same situation, but now we want to find the electric field. And so we're going to use Gauss's law. And so Gauss's law says that the integral, closed surface integral of E dot dA is equal to the charge enclosed over epsilon naught. So let's imagine now that we're within the sphere, big R, we're less than big R, and so we want to find the electric field. Well, we know that because of symmetry, we can pull this out and we can add up all the dAs, which will be a surface area. Now, what is my charge enclosed? Well, from the previous problem, I know that this is 30 r to the fourth power over epsilon naught. And so this is E times, well, this is an area. And what is it? It's 4 pi r squared. It's the area of a sphere. And that's going to be 30 r to the fourth over epsilon naught. And you can see here that we've got a 2 here, that's going to go away. That's going to become a 2. And what we have then is E is equal to 30 over 4 or 15 over 2 pi epsilon naught times r squared. And so that is our solution for E as a function of r. Okay, and this is E as a function of r when r is less than r. Now, what happens when I'm all the way here at the outside of my circle? Well, I'm going to have the same Gauss's law, E dot dA, and this is going to be, again, we said this is 30 r to the fourth over epsilon naught. That's my charge enclosed. And so this is E times 4 pi r squared is equal to 30 r to the fourth over epsilon naught. And we can see once again that my r's, this goes away. I'm sorry, this is a capital R. Let me make that a capital R. Okay. And so we can say that this becomes a 0, this becomes a 2. And so then we get E is equal to, again, 15 halves r over pi, 15 over 2 pi, and we have r squared, capital R squared over epsilon naught. Our last part of the problem, before we hand it back to Frisco, Texas, is r is greater than r. Now, here's one thing I want you to stop integrating and stop using Gauss's law. Because why? Because we've got a spherically symmetric charge, and now I am past the point of any charge increasing. And so what does that mean? That means that I can use my formula for the E field from a point charge, and that's KQ over R squared. We did that a few days ago. Well, K, and this is on your formula sheet, is 1 over 4 pi epsilon naught. We talked about it the other night. Q, we found out, was r to the fourth. Q is 30 r to the fourth. Okay. And r squared is going to be, well, wherever I happen to be. And so we can see here that we have the 30, and so we have 15 over 2 pi, and we have r to the fourth over r squared. There's an epsilon naught in there, and I don't want to forget that. That's how we do this problem. Now, if I were you, I wouldn't be able to follow it that fast. I have trouble, but we want to get a lot in tonight. So don't forget, take a second, pause the video, try it, and see what you can do with this. And it should make a lot of sense to you. We're going to hand it back to Frisco, and I think we've got some real doozies for you coming up. Stay tuned.
So hopefully not too hard though. So we're going to do a couple, and I'm going to try to adjust them to tailor to us practicing a little bit more towards this year's exam. So I took a question from, I think it was 2 or 3 years ago, the E&M exam, and I've changed it a tiny bit to kind of make it a little bit more conceptual to have you writing and thinking a little bit more. So we have here a very large non-conducting or insulating slab with a uniform positive volume charge density rho naught. It is fixed with the origin of the XYZ axis at its center, as shown in the figure above. The thickness of the slab is D, the length is L, the width is W, where L is much, much bigger than D, and W is much, much bigger than D. So the large faces of the slab are parallel to the XY plane. So what that means is it's very, very like wide and girthy, right? But not as much height-wise. So we can think of it almost like it's infinitely long compared to its thickness. And so that can tell us a little bit too about the electric field and the electric flux. That's just a little bit of a hint. So I want you to tell me these two things. You're going to write down for me what Gaussian surface you could use to determine the electric field at points R and S within the slab. So this is our side view here, and we can see that we have point R and point S within that slab. And I want you to tell me what kind of Gaussian surface could you draw to determine what the electric field is at either of those points. And then which of the surfaces on your Gaussian surface would have electric flux. So what surface would you use and which size would have flux? I'm going to tell you there is more than one option actually with this one. Okay, so remember one thing we said you can do is you can use the same symmetry as your charge. So this charge is a rectangular prism. So the thing that comes to my mind first would be to draw a rectangular prism that goes through R and S. Okay. And then the second thing is which of the sides of my rectangular prism would have. So I'm going to draw it a little bit here too so we can kind of see that shape. So which sides of my Gaussian surface would have flux? Well, if this is very wide this way and this way, well, then we really couldn't take those into account as having flux. So the only sides that are going to have flux is at those top and bottom sides of my Gaussian surface, right? If we're looking at it this way, it would be the top side and the bottom side here. Okay, what other surface could you use? Well, I think when Roger did his slab the other day, he used a cylinder. So there are some people that like to use the cylinder instead for their Gaussian surface on the rectangular prisms, and that's totally acceptable also. It's actually what they gave you on this, right? So this problem did not have originally that first part there. It kind of went right and gave you these shapes, right? So let's consider a Gaussian cylinder with a cross-sectional area A and a height h, right? So if I draw it big over here, we've got this cylinder that has a surface area A and a height of h that is positioned along its axis as shown in the figure below. So if we look at that side view, we can see it here that goes through R and S. So I want you to describe the direction of the electric field at point R and at point S, or state that it's zero at any of those points. So which way is the electric field at point R? Which way is the electric field at point S? What's that first thing you should be asking yourself? Is it positive or negatively charged? And if we go back to the beginning of the question, it is positively charged. So if it is positively charged at point R, the electric field should be pointing away or up. And at point S, it should also be pointing away or down. So at point R, you could say up. You could say in the positive Z direction. And at S, you could say down or negative Z direction. Okay, next step, let's use Gauss's law to now derive some expressions. Let's find what the total flux is through the Gaussian surface shown. So if we want to know what the flux is, how do we get flux again? We know it's either side of Gauss's law, right? So I'm going to write them both down and then we're going to look at which side we should use. Okay, and like I said, let's always try to use this charge side if possible, because the only thing we have to worry about is the charge. We don't have to worry about what the field is, because we'd actually have to know to actually find the flux, we'd have to know what the field is and what the surface area is. That's not as difficult, but we don't know what that electric field is yet. So we got to use that right side. So we got to find what is the Q enclosed on this Gaussian surface, right? So if this is a cylinder, we know that the slab has a uniform charge density rho, right? Volume charge density. So what does that mean? Well, volume charge density means rho naught, which is equal to Q over the volume. Okay, now they don't give us the volume of the cylinder, but they do give us that the cylinder has an area A and a height of H. So I can say, well, what is the H? It is, right, H over 2 here and H over 2 here, so that's just H. So I can say really Q is equal to rho times the area times the height. So if we plug that in here, then our Q enclosed is going to equal rho naught times A times H over epsilon naught. Okay, and then next, let's derive an expression for the electric field as a function of Z for any position, right? So this is kind of like what we were doing the other day with like as a position of R, but here we're using that Z plane here. So as a position of Z, we want to know, if I zoom way in here, right? As we go out here, give us a function for the electric field and show that it is equal to E, which is equal rho naught Z over epsilon naught. So we're trying to derive and get that one. So where do we always start? We start at the start, which is Gauss's law. Okay, we're going to address our two sides. So what is our surface area here? We used that cylinder. Which of the sides, though, had flux? Remember, we're only going to look at the sides that have flux. We had no flux out those sides because that is so large. So really the only place we had flux were those top and bottom parts of the cylinder, those two areas. So really I can say that this is E times 2 times the surface area, which equals, well, let's plug in our charge, but we need to have it as a function of Z, right? So we got that our charge is rho times A times H. So let's look though at what that H is. We want it as a function of Z. Well, as I go out from the center, again, if I zoom way in here, if I go out from the center here, well, if I'm going out a distance of Z here, my whole surface though is also changing a distance of Z on the other side. So what would that total height be? It would be 2 times Z. So when we plug in for our Q here, instead of saying H, we need to say it's really 2 times Z. So this is rho naught times A times 2, not Z, 2 times Z over epsilon naught. Okay, well, we've got an A here, I got a 2 here, and a 2 here. So that leaves me that E is equal to rho naught times Z over epsilon naught. Okay, so we start with Gauss's law. What is the shape of your Gaussian surface for that surface area? Do all of the sides have flux? If not, you're only looking at the surface areas that have flux to plug into Gauss's law. And then what is your charge that you're going to enclose? Okay, so let's look now. Instead of just our slab, we're going to put that slab in between two parallel plates. So our large metal plates are separated by a distance of 0.01 meters, which is approximately the thickness of the slab, right? So it's taking up the whole space in there is what that means. But the slab does not contact either metal plate. The metal plates are charged, and they give us those charged surface densities. Remember, sigma. The first thing I want you to be thinking about in your head when they give you these is that per length, per area, or per volume. So this is sigma, and sigma is charge per area, right? I'm always thinking these things, jotting them down as I'm reading and identifying. So top is negative, bottom is positive. What sticks out in your head when you know which plate is which charge? Well, I'm kind of thinking in my head which way the electric field is in between those two plates. I'm not going to draw it in yet because I want you to do this next part. Assume the charge distribution remains unchanged by the presence of the charged plates that the slab and the slab's volume density is. So now they're giving us rho, but we're still just going to keep everything in terms of symbols. We're not going to plug and chug because we know you're not going to be doing that on the exam. So the magnitude of the electric field inside the slab is 0 at the x-axis at some position z naught. So they're saying somewhere along the z-plane, the electric field is going to be equal to 0. Okay, so you're going to tell me where that is. Where would the electric field be 0? What would have to be true in order for it to be 0? And you tell me, is it greater than 0, meaning it's in the top half here? Is it right at 0? Or is it less than 0, meaning in the bottom half of the slab? So I want you to take a second, think which way that would be, and how do you know that that's where it is? Justify that answer. First thing you better be doing is drawing me the direction of the electric field due to the slab and due to the plates. Okay, so we already know the slab, so let's do that first. I know that the electric field of the slab on the bottom portion is going to be downward. I'll label that ES. And I know it's going to be upward in the top portion because this is positively charged. Okay, next thing I'm going to look at then is my parallel plates. This is negatively charged plate. This is positively charged plate. Well, the electric field is going to run from the positively charged plate to the negatively charged plate, which means everywhere in here. I draw a couple of them so we can see it, maybe one right next to these others. The electric field is upwards. If you look at these top, what do you notice about the electric field due to the slab and the electric field due to the plates? They're in the same direction. What would we do? We would add those together. So it's going to be a pretty big, comparatively, electric field in that region. Okay, what if we look on the bottom half though? In the bottom half, we've got electric field downwards and electric field upwards. What would we do with those? We would subtract them. And if we're going to subtract them, that's going to be in our region where that electric field will eventually become 0. So that would be at the E is less than 0. So what would we want to say? What would be some key words that we would want to use in order to explain this, right? Where are we going to get as many points as possible? Well, the first thing we want to know is we want the electric field from the slab to be equal to the electric field from the parallel plates. And I'm kind of shorthanding here, right? So first thing we want to say is we want those two electric fields to be equal in magnitude, but opposite direction. And then we would explain how we know which of those directions are, right? We know the electric field is going down in the bottom half due to that positively charged slab, and we know that all the time the electric field is uniform and upwards due to those two plates. So where is the region where it would cancel out? It would be in that bottom region. Okay, now let's actually find where that would be equal. So we already started that right here. We know that the electric field due to the slab has to equal the electric field due to the plates. Well, we nicely already have our relationship, right? They gave it to us. And we derived it. It's that the electric field is rho naught times Z over epsilon naught. But if we're looking for the exact position, we want to say that it is rho naught times Z naught over epsilon naught. It's an exact position Z. That's got to equal. Now we've got to look really quick at how do we find the electric field due to those plates. So I'm going to erase some of this so we can zoom in and we can Gauss one side of these plates. So if this is positively charged, if I want to find what the electric field is in this region here, well, I'm going to enclose that plate and I'm going to use Gauss's law to find what it is. Okay, we're going to address our two sides. First of all, is there flux everywhere? And this is where a lot of people kind of get thrown off here. If we look at these plates, this is negatively charged. So we've got electric field coming in towards it everywhere, even over here, right? So, and really when we look at like the grand scheme of things, the distance between these two plates is very small compared to like the area around it. And so, but there's also that electric field going away from the positive plates. So if you look, and let me keep going, on the outside, we can say that that electric field is pretty much 0 compared to that electric field inside. The electric field outside our parallel plates is 0. So what is the only surface that's going to have flux? That's going to be my surface here, right? There's going to be no flux here. So we just have one side of our Gaussian surface that's going to have flux when we're enclosing that plate. So if we're looking at the Gauss's law here, for that plate? Well, this is just going to be one of those areas. And why that doesn't matter is because we're going to plug in that Q over area is the charge density. So Q is equal to sigma times A. So it doesn't matter what that surface area is. The bigger my Gaussian surface, the more charge I'm enclosing. It's proportional. So this becomes sigma times A over epsilon naught. A's cancel. The electric field due to a parallel plate is sigma over epsilon naught. So we can plug that in over here that this is sigma over epsilon naught. So what happens with our epsilon naughts? Those cancel out. If I want Z, Z naught is going to be equal to sigma over that charge density. Interesting, right? It's that ratio of those charge densities. Okay, so being able to pick and describe your Gaussian surface and where there is flux, I think is going to be really important this year. So always keep those things in mind. Okay, and then the next thing I have here is not Gauss, but it's just a little bit more kind of fun with charge to kind of wrap up our charges and forces and fields. We're going to revisit it, but we're going to move on to electric potential tomorrow. So we're going to do this problem here that I found. And it is we have two pucks that are connected by a non-conducting rigid rod and given a positive charge QA and QB, right? Both of them given positive charge. I'm going to label that. The pucks are set on a smooth, frictionless table along with a fixed puck C, right? So this one's not going anywhere, which has a negative charge QC. So in case one, we're going to say that QB is equal to 1.5 times QA. And it's free to, the rod is free to rotate, right? So our puck is fixed, but our rod is free to rotate. So I want you to draw me the forces that are acting on A, right? So draw arrows representing only the electric forces exerted on A and B. So you don't have to necessarily label them, but it is necessary that each vector be a distinct arrow and starts, right? So we're going to do that part quickly. I really want to focus on kind of the argument part here. So if we look at A, well, A has how many different charges that are interacting with it? Well, there's two interactions here. We have the interaction between A and B, which if these are both positively charged would give us an electrostatic force to the left. And it's also interacting with charge C. So if we look at those two charges, then there'd be an attraction. But we want to look at how far they are apart, right? So I'm going to draw some distance is in here. So if we count the squares, this should be 6 squares here, and this is 6 squares. Well, this is more than 6 squares. And we remember that force, if we're looking at point charges, was K QQ over R squared. So if this is a bigger distance between them, then I know this force is going to be a little bit smaller. So I'm going to draw it a little bit smaller here. Then if we do the same thing for B, well, if B is creating a force on A is creating the same equal but opposite force to the right on B. And B is also interacting with C, attracting it, and it's got the same distance, so it will be the same force. So, question is, in which direction does the center of the rod accelerate at the instant shown in the diagram? Does the rod rotate clockwise or counterclockwise, if at all? And justify your answer using the forces you drew, right? So this could be something you would see on the test. You probably wouldn't have to like submit and turn in your free body diagram, but you're going to have to draw these free body diagrams to be able to explain and justify your answers that you're going to be writing. Okay, so I want to give you just a couple of seconds here, compose your thoughts, write down some important good physics words to explain which way is the center of the rod accelerating, and is it going to be rotating at all? And how do you know? Okay, so what do we go back to know if the center of the rod is accelerating? Well, that goes back to net force. And how do we know if something is going to be rotating or have angular acceleration? Well, that goes back to net torque. So let's go back and look at these forces. Let's look at our ups and downs and lefts and our rights. Do we have a net force? Okay, well, if we look at our A and B, well, if this is a positive rightward force and this is a leftward force that we could say negative, and we know they're equal in magnitude, then I can say, well, if I added force due to A and B to A, that those would equal 0. So really what we're looking at are our other two vectors, right here and right here. And what would those sum up to? Well, I've got an positive X component and a negative Y component to here, and I've got a negative Y component here, which if I added those together, we'd get a big downward, but also a rightward force. So our acceleration would be both to the right and down. Okay, now let's look at torque. If we look at the center of that rod, I'm just going to redraw it right here. Okay, we have to look at both like where those forces are acting, but also the magnitude, right? Because remember, torque is R cross F. And so if I look at the forces again here, well, if I look at the right-hand side, then we've got a torque R cross F here, right? No torque here because that is acting through that pivot. But I do have a torque R, the half of this rod, times that force going downwards towards C. And if I look at this one, I've got R cross F, which would only be this component of the electrostatic force, right? Again, no torque here because it's acting through that pivot. So if we look at the magnitude though, which one of these would have a greater magnitude? That would be the force on the right-hand side here, which if we actually follow through R cross F, we can easily see that that's going to give us a clockwise torque. So we still can have torque with our charges. This is what we call a dipole here. So it would be a clockwise torque because there is a net torque on that right side. Okay, so we're going to stop for there today. And if we have time, sometime we may come back and do the second half of that. But hopefully tonight kind of helped concrete some of those questions you had with Gauss's law. And I did have on here, though, what we are doing the rest of the week, I think. Yep, here we go. So here's our schedule for the rest of the week. Tomorrow, we are going to do electric potential with point charges. Then we're going to do electric potential and electric potential energy. And then we're going to go into back and revisit those kind of other distributions we saw the other day with like a line or an arc along with electric potential. And then we're going to do concentric conductors to lead us into capacitance. So hopefully you will join us tomorrow. My name is Kristen Gonzalez Vega from Frisco, Texas.
And my name is Roger Siegel from Sarasota, Florida.
All right, you guys have a wonderful night.